that is the parity per column of binary bits. So what I mean is, if I have this board, what is the parity? This is 1, right? I'm transforming the counts in binary. 2 is 1, 0. So the parity is just looking at this column, looking at this column. The parity is per column 0 if, 1 if, 0 if what? For that column. Even number of ones. This is if odd. Parity is essentially a XOR, right? Think about it. Bit 1 XOR bit, let's say B1. B1 XOR B2, those are this is a column, right? XOR bit 3, XOR, so far XOR bit n. This XOR, it's gonna end up in 0 if I have an even number of ones, and it's gonna end up in a 1 if I have an odd number of ones. That's what the parity is. Parity is an important function in computer science. So for this board, parity will be what? 1, 1, right? Because if you look at every column, there's 1 on this column and there's a 1, 1 on this column. How about this board? How this board gonna look, the parity? What are the counts? 1, 0, 1, 0, and 1, 0, 0. So the parity in here is 1, 0. The parity is a sequence of bits, each bit corresponding to, everybody follows me? I have 1, 1 on this column, so that's a 1. I have 2 1s on this column, so 1, 1 becomes 0. And I have no 1s on this column, that's a 0. How about this board? What is the count? This is, let's put another 1, make it more interesting. 4 is 1, 0, 1, 0, 0. This is a mistake, right?
Yeah. It should be
1, 1. Sorry, I went ahead of myself. So what's the parity now? 1, 1, right? 1, 0, 0. This is a 1, 0. 1 is a 1. Another 1 is a 1. This is a 1, 0 again. So what do I get?
1,
0, 0, 0. 1, 0, 0. That's how this parity function works. So the theorem is several parts. The most important part being my strategy is what? Leave the parity of the board. Leave meaning after the move. That's what I mean by leave. After my move, I want the parity to be
0.
0, 0, 0, 0. This is a winning strategy. If I can do this after every one of my moves, leave it in 0 parity, I'm going to win this game. To prove that, we need to prove the following statements. Number 1, if the parity is not 0, 0, 0, 0, then there exists a move to make parity 0, 0. In other words, if the other player doesn't leave me the board at 0 parity, any board that's not completely 0 parity, I have a move to make it, to bring it there. Number 2, if I leave parity 0, 0, 0, 0, then the other player will leave board not with parity 0, 0, 0. So in other words, if I make this move, the opponent, my other player, cannot do the same. If the board comes like this, for example, 1, 2, 3, I believe it's such a board, right? 1, 1, 0, 1, 1. The parity in here is 0, 0. If I leave it like that, whatever move my opponent does, that board will not have parity 0 everywhere. So this one says, if my opponent moves and is not living in 0, 0, 0, I always have a move to bring it at 0. And if I bring it at 0, my opponent cannot do the same. And number 3, if the parity is not 0, 0, 0, 0, it is, sorry. If it is 0, 0, 0, game cannot be won in one move. So in other words, when after I make my move, I leave it to 0, 0, 0, 0. Unless I finish the board, I took everything of it. If the board still exists, the other player cannot win because there's no one single move that can do this. That's quite easy to see. If the parity is 0, if the board is not empty, what must happen? If a parity is 0 and the board is not empty, how many rows must be there on the board? Yes. At least 2. There's no way to get the parity 0, 0, 0, 0 with only one row. That's not empty. So there must be at least 2 rows. Therefore, my opponent, who can take pieces only from one row, cannot finish the board. But we need to prove these other things, and the necessary mathematical functions are given in the recitation paper. Those last 2 sheets, like XOR per bit, will allow you to prove this. Okay? I'm not going to do those proofs now. Just want to recap where the square game is. The strategy is to leave the board at 0, 0, 0, 0, and to prove those 3 things.
What does it say above the second parity?
Here,
Yeah.
if I leave board in parity 0, 0, 0, 0, then my opponent has to move it away from that. So that's the first thing we need to do before moving on. The other thing that I want to do is the countability of infinite sets. We can't really do this in a general mathematical way, but I want to show you two examples of countability. One is z, actually 3 examples. The other one is n squared, and the other one is q. So we don't know enough mathematics to define countability correct, but we can definitely define it intuitively. Countability, a set A infinite is countable if it can be arranged. I'm going to say arranged, that's an informal word. I don't mean it in an exact mathematical sense. Arrange in an order that is countable. That is, let's not do a recursive definition countability with countable, that is enumerable. Mathematically, what that means, there is a one-to-one map between that set A and the set of natural numbers. So as long as I can enumerate a set, infinite set, in a way that's clear, here's the first element, here's the second element, here's the third element, fourth element, and so on and so forth, and it's clear that in that enumeration, every element shows up. and shows up exactly once, I call that today in this class countable. For mathematics, that's the right intuition, but we need a little bit more formalism. So what I mean to say by enumerable here is literally I'm going to say first in A, second in A, third in A, and I'm going to make some dot dot dots. I need dot dot dots because the set is infinite. I can't enumerate everything. But this has to be clear that everybody will show up. So let's take Z. Can we write Z in that informal enumerable way? Is there a way to write Z starting somewhere such that every element will show up exactly once? Yes?
0, 1, -1, 2,
2, -2, 3, -3, 4, -4. I mean, I know this is not rigorous mathematics, but I think everybody can see every integer is going to show up in this list somewhere, right? Hands up, who's with me? Now, can we also see that every integer is going to show up exactly once in this sequence, right? So that counts as countable. Now, if I really want to build a map between Z and N, okay, I'm going to say this is first, this is second, this is third, fourth, fifth, right? And now, why is this okay? N doesn't start with 1, right? N starts with who? 0. Well, this is not quite ready yet because it maps the Z's into 1, 2, 3, 4th, but what if N also includes a 0? What do? I move everything by one spot to make space for the 0, right? So instead of doing it this way, actually that's not bad. Let me leave it here. That's still countable. I could say zeros, first, second. Zeros not really an English word, but we computer scientists, right? So I make space there for 0, so I include 0. Now I really have a map between Z and N. You can see it's 1-to-1 mapping, right? Everybody 1-to-1 correspondence. Fine. That's easy to see.
So by the 1-to-1 correspondence, we want to capture the fact that there's nothing between the first and second items?
No, we want to capture the fact that everybody in N has a unique correspondence in Z, and everybody in Z has a unique correspondence in N. So there's no one that goes to many, or somebody that's not into the 1-to-1 mapping. Somebody missing from the map. What if I say I want the N even? So my set now, this is the set of natural numbers. That's my basic countable set. I want to count can I count the even numbers? How do I do that? How do I enumerate the even numbers? I know I'm asking a trivial question. 0, 2, 4, 6. This is obviously countable because this is a sequence that includes all the even numbers, and I can point at this, the first element, second element, third element, fourth element, so on and so forth. What if I want the Z even? Is that countable? The set of all integers that are even. How do I do that? 0, 2, -2, 4, -4, 6, -6. This is also a countable set. Everything that can be arranged in a way that gives me a clear map between the natural number of the order 1, 2, 3, 4 and those numbers. As long as I can guarantee that every one of my numbers appears somewhere in the sequence, it's countable. Okay, that was easy. How about N squared? Who's N squared?
The set of X and Y.
The what?
The set of X and Y, right?
Right, so this is a size of pairs, right? With the property X and Y are natural numbers. So what are those pairs? Those are like 0, 0, 0, 1, 0, 2, 0, 3, right? Keeps going. 0, 4, so on and so forth. Then it starts with 1. 1, 0, 1, 1, 1, 2, 1, 3, so on and so forth. Then 2, 0, 2, 1, 2, 2, 2, 3, so on and so forth. Then 3, 0, 3, 1, 3, 2. Every one of these, so on and so forth, goes to infinity, right? Because every 1, 1, 1 can be paired with every other natural number. So then I have dot, dot, dot. At some point I have, say, 100, 0, 100, 1, 100, 2, dot, dot, dot. And that's not the end. There's still an infinite number of rows, right? It's not just infinite in the column sense, it's also infinite in the row sense. Is this countable? Can we arrange these pairs in a way, just like we did here with elements, we want to arrange those pairs now in a way that they form a sequence we can clearly point to who's first, who's second, who's third. Yeah, all the way in the back.
Why is n squared xy rather than just x squared?
This n squared, you can define it like that, but the standard notation is n times n, Cartesian product.
So any natural number times any natural number,
Not times as in product, as a Cartesian product, which is make a pair with one element from here and one element from here. He's not wrong to say, wait a minute, n squared can mean three things. It can mean this Cartesian product, it can mean x times x, right? And maybe it can mean some other things. I mean, it can mean maybe all x times y values, or maybe just the ones that are squares, x times x. So those are other possibilities for what n squared might mean. But typically for sets, if we don't say anything else, the default notion when we say n squared is the Cartesian product n times n. R squared is a pair of real numbers. Z squared is a pair of integers. So this is not a product, it's a pair of two numbers. Now back to my question, can I somehow organize all these pairs in a way, in a linear sequence that allows me to clearly say who's first, who's second, who's third? Yes?
When it's in like a grid like that, you can like go diagonally. And like,
Right. So I think you're saying, how about we call this one first? Which is second?
0, 1.
Say this is second. But the problem with this, why this enumeration is a little tricky, and he's got it right, is that if I start enumerating the whole row, I'm using up my enumeration resources, and I only enumerated the first row, right? If I say first, second, third, fourth, so on and so forth, I will never finish the enumeration of the first row, which means I never got to the second row. So clearly I can't just go by a row, finish that row, move on, because I'll never finish that row. That's a countable sequence in itself. I could go by the column, but then again, if I say go down by this column, you can never finish enumerating that column, therefore you never reach the second column. Question?
Couldn't you just go 1, 2, 3?
I think that's exactly what he was saying, right? His point was, if I got it correctly, that the third element can be here, and the fourth should be where? Where's the fourth?
Top right.
Here? Or here?
Either
Or
one.
where? Which one?
If you're going to be consistent, you start at the top right.
Yeah, 0, 6.
So I could start in here and go this way. It say this one is the fourth. This will be the fifth, sixth. And then I think you guys are saying this is the seventh. This is the eighth, ninth, and 10th. And so this way, now, can I enumerate all the table? Back to my what enumeration mean. Am I guaranteed that every pair in this table eventually is going to show up in my sequence? Am I? Because no matter where the pair is, in row, a pair in here will be row 100 and column 925. Could be, right? That pair, if I do this zigzagging into the table, eventually I'm going to reach there. It might be a very big number. The index of this pair in my enumeration might be 900,000. That's fine. Eventually I'm going to get to it. So that's how I can enumerate n squared. Therefore, n squared is countable because I can enumerate its elements. Right? N squared is countable. But see, n squared still feels discrete. What I mean by that, informally, is that there is a lot of space between these elements. Any two elements, they clearly apart, right? How about Q? Q is a set of rational numbers. Q doesn't have this set apart property. Elements of Q can be arbitrarily close, right? Rational numbers can be very, very close to each other. In fact, arbitrarily close. Can I enumerate the rational numbers? Yes.
Kind of the same like table sort of numerators as well as the same denominators.
Right. So I think what you are saying is those are the sets of fractions, right? A, B being integers, and B not zero. That's Q. All the fractions that I can get from integers. And you're saying, take all the fractions and put them in a table similar with that one, right? So how can I do that? Take all the fractions and put them in a table. Let's try that. What's the first one that goes in the corner? 0, 1. That's the first fraction, so 0 by 1 then.
Yeah.
Okay, what goes in here? 1 by 1. Okay, and what goes in here? But this is all just the positives, right? I mean, we have to, Q has also negative numbers. We get to put those in somewhere too. So there's two problems here. One is that we miss the negative numbers. That's one problem. We miss the negatives. What's another problem in this table as far as enumeration goes? Somebody else. There's another problem, yes. I have a lot of duplicates. These rational numbers 0 by 1, 0 by 2, 0 by 3, 0 by 4, they're actually the same rational. So how can I fix this? I have two problems. The negatives are missing completely and the positives are actually duplicated.
For the negative one, can you change the definition so that A and B are integers such that B is not 0, B is greater than 0?
Right, B could be positive, she's right, because I don't need both numerator and denominator to be negative. If I fix the denominator to be positive always, and the numerator either positive or negative, I get all rationals that way. But still, I don't have any negative values in this table as of now. Yes?
You could do the same thing we did with the set of integers earlier, where,
Right.
where after we do 0,
For the ones that's the numerators, that goes on this line, right, on the columns, instead of putting the natural numbers there, I just enumerated earlier all the integers, that's what he's saying. So why not use that order of the integers to not get only positive numerators, but get both of them? So how would that look? 1 by 1, what's the next one? What's the next one? What's the next one? 3 by 1 minus 3 by 1. And now I've got in here, what? 0, 1, minus 1, 2, minus 2, 3, minus 3, 1, minus 1, 2, minus 2. That solves that problem, right? Now I have the negative values in. I still have the problem that if I apply the same strategy, if I go here and I say, okay, just go zigzagging this table, I'm going to get duplicates. So that's not a one-to-one map because the value 0 will show up so many times in my sequence. Yes?
We should start with 1, 1 at the top left.
Start with 1, 1?
Yeah.
And ignore the zeros? Or
Yeah, ignore the zeros.
so just kind of delete this column? But I get no 0 at all.
Because each problem will The column and the row will both choose 0.
So where do I start? Here?
So you start with 1, 1.
I start here, then? That's the 1. What's the next one?
1 out.
This one. That's the second one.
Sure.
What's the third one?
1/3.
Here.
Yeah.
Fourth one?
1/4.
That's not going to work if we keep going down. Because it's the same problem like here. Remember why we couldn't do this table going all the way down or all the way to the right first? Let's recap that idea. Why we couldn't just do the first column first and say, then go to the second column? Because I don't have enough enumeration power to just move after the first column. I have to go zigzag, right? Hold on. Hands up with me why we had to go this table in a funny way and not just the first row, second row. That's the same what's going to happen here. We can't just put a column first, because then that column is going to take all the enumeration ability I have. Right? If the column is infinite, by the time I finish and move ready to the second column, there's no time I finish, because I can't finish. So that's not going to work. We can't do this. We still want to go zigzagging, but zigzagging, wherever I start, there's not just 0, by the way. 0 is not the only duplicated value, right? Every value is duplicated in here quite a few times. Right? That 1 by 1 is the same as 2 by 2, is the same by 3 by 3, right? That's all the same value. So how do I solve this problem? Yes?
Would you say that A and B are not divisible by the same number unless it's 1?
You mean when I build the table? Or when?
And then your definition.
In Q? You want to add something here, which is
Saying
A and B are co-prime.
Yes.
We don't know what that means yet, sorry. Relatively prime. What does co-prime mean? Relative prime, aka have no common factors. So that will solve what problem? That will solve the problem of 3 by 3, right? Because 3 by 3 really is the same as 2 by 2, but if there's no co-primes, 3 by 3 is not in this table. Assuming that works, I'm not saying it does. Assuming it does, then I'm not sure, can I define what goes on the line? So, see, the way I build this line is very easy, right? What do? I fix the denominator, and then I enumerated z in this order for the numerators, right? That's every line is built that way. Now what he's saying, don't include 3 by 3 in here. So what's the next one on this line? If 3 by 3 is not there, how about minus 3 by 3? Is that there?
Nope.
So 4 by 3?
Yeah.
Even if this works, I'm excluding the numbers that have common factors, the A and B's. I have then, I need a way to explain what this row is, right? It's not obviously anymore that it's an enumeration of Z. And would that work if I remove all the co-prime values? Do I really get no duplicates in the table? So what the duplicate is? A duplicate is when A by B equals C by D, right? That's what the duplicate has.
You still have the 0 duplicates.
I still have 0 duplicates, so maybe I can say only the first line starts with 0, the other ones don't have 0 in them. I don't know, something like that, say. So cut those zeros here. And is it the case in here that if this is true, one of the fraction does not check out the co-prime? Is that true? Is it really true that if I put this condition here, okay, I can't get duplicates? So in other words, is it true that from here, either A, B have common factors, or C, D have common factors? That's a great question for the final exam. There's two fractions of integers, A, B equals C, D. Show that it's not possible those to be co-prime and those to be co-prime. I don't think that's a trivial problem.
Wouldn't for AB to equal to for A or B to equal C over D, wouldn't it have to be AB equals like a constant times?
But the constant is not an integer, right? It's some value V, which is 2.713589, right? It's not an integer. That's the whole point of rationals. So is that a simple thing to prove, that if two fractions are equal, one of them must have some coprime factor?
So you have to specify that A is not equal to B and B.
Right, and A is not the same as C, and B, B is not the same as D. Like, it's not the same form. I like the idea, I'm just not sure that's a simple thing to show. Either A, B have common factors, or C, D have common factors. So in other words, it's not possible A and B to be relatively prime and C and D to be relatively prime. That's what he's saying, that if you eliminate all the ones that are not coprimes, you can get only value exactly once. So you can't get the value twice. Hands up who's with me. Well, we have to table this problem for 3 weeks later after the meter when we do number theory and see if we can solve it or not. Or you can solve it right now if you want, if you can. Any other idea for how to enumerate this table? So I think this will do it if this is true. I don't know if it's true, but if this is true and we can prove it, then I think this will work because every value is exactly once in the table. Yes?
Couldn't we just simplify it and like do the thing where you only count 0 once and just move on to like 1 over 1, all that stuff, and do the diagonal, but we just don't count it because it's already happened?
Don't count it means what?
Don't assign it a value.
Like skip it.
Skip it, yeah.
I see. That's another idea. Leave the duplicates in. But every time my zigzag formula hits a duplicate, skip. Just keep going. Would that work? To say, okay, 0. I can include a 0 that way, right? If I do that, I can have the zeros back. And say, okay, 0. Have I seen 0 before? No. Put it in. 1 by 1. Have I seen that before? No. Put it in. Then I get to this 0. Have I seen 0 before? Yes. Skip. This is not counting us. So the elements will be this one, this one, this one's a skip, this one's a skip, this is the next one. Minus 1 by 1, have I seen that? No. So this one is in. I move in here. 2 by 1, that's good. Minus 1 by 2, is this good? Yes. 1 by 3? This 0 by 4? No. How about 1 by 4? Minus 1 by 3? 2 by 2? No. So see how I'm skipping this and then keep moving? Would that be an enumeration that guarantees every value rational appears in this enumeration somewhere? Because I only skip the ones that I've seen before. So a value, it's either in the list or it was before in the list. So this is not quite complete, but I think we can agree Q is countable. That way, with a lot of tweaks and hacks, what to skip, what to not skip, how to deal with fractions that you want to put in a table, not put in a table. It's not as easy as the n squared. How about, I have 2 questions that I cannot answer, but I want you to think about them. I have 2 more sets to ask if they're countable or not. The first set is n cubed, which like before, we're not cubing anything. We're just creating triplets. This is the set of x, y, z with the property that x, y, and z are natural numbers. So those would be things like 0, 0, 0, 0, 0, 1, 1, 0, 0, 1, 0, 1, so on and so forth. All the possible triplets. Is that countable? Can I build some sort of gigantic table and counting it?
You do like a 3-dimensional cube and you start in the corner and you spiral around.
Right, so I should apply this idea in 3D. If I make a cube out of it, 3-dimensional n, can I go in a corner and then spiral, but I have to spiral not just in 2 dimensions, I have to spiral all 3, right? So when I advance from that corner, I don't leave everything not touched. And you think you can get the whole cube that way?
Yeah.
Okay, so I think it sounds interesting, yes.
So you can just use the order that you already have for like mapping n squared.
Very good. That's a much more elegant solution to say, if you counted n squared already, that's a countable set. And you counted n is obviously countable, 0, 1, 2, 3. Think of this as n squared times n. This is countable, this is countable. Now this is a 2D table, because I've already counted these elements as first, second, third. So I replace every one of these n squared elements with the one-to-one mapping in n. So now I have another 2D table now that I have to count. So I can apply this idea recursively. If I can count n squared, and I know how to count something times something with a table, I'll count n cubed. Hands up who's with me on that. Very good. So that's one thing to think about. The other one is the set of real numbers. Can we count the set of real numbers? Is there a way to enumerate all the real numbers? So there's two problems to that. This is a way more difficult question. The first problem is we don't know what this is, right? What is the real number? Like mathematics starts by defining first n. In fact, it does not define n. It says n is a natural axiomatic set. First sheep, second sheep, third sheep. My neighbor has 3 more sheep than me. It just built in our human nature to count things. We don't define n. But after n, we can define z very easily. We can define q very easily, right? Just with n, we say fractions or negative numbers. It's not that easy to define r. Starting from n and z and q, now that I have those defined, how do I get to r? Yes. You. The wall. Yeah, the wall.
Okay. Okay, so you can do your table, and then for like across the top, you can have all the integers, and then down for like each row, what you do is you take an integer and just make like that top integer point, and then whatever the integer on the left is.
Let's see. That's a countability of r? That's how I count r?
Yeah.
All right. Let's see. So he has an idea for how to count r, and I say I don't even know what r is, but let's see where we're getting with it. What's the left corner of the table?
So you would, like across the top of the table, you would go 0, -1, 1, yeah.
That's the integers, and then here is?
And then there you would, like across the other side of the table, you would do the same thing.
Here, 0, 1, 2, 3.
0, 1, -1, 2, 3. Yeah, and so that the top left corner would be like 0.0, and then you have the next one over is 1.0.
This is 1.0? This is minus 1.0?
Yeah.
2.0, and in here we get what?
0.1, 1.1, -1.1.
I think you mean to say these are the decimals.
The column should just be the naturals, not
This one is the national, okay. So 0, 1, 2, 3, and at some point in here, I think what he means, those are the decimal part of the number. Like if the number here is 7291, right? He means to say this column will be -1, right? 0.7291. Is that your idea, right?
Yeah.
It's saying, look at the left side of the dot is the integer that's on the top, and the right side of the dot is whatever the natural number is on this here. So the table looks like this. Right? So if I have another number here that's 335, you know, when I get to the point 3, what do I get here? 3.35. See, his observation is that for every number that can be written in decimal, both the left side of the dot and the right side of the dot are integers. So, right? But is he getting here what kind of numbers? What are those? Are they real numbers? Oh, of course they are. But are all the real numbers, or he's just getting the rationals again? I think all those numbers are rational numbers. Right?
Yeah.
Because everything is an integer divided by 10 at some power. So I think that's a cool idea, but it solves counting Q, not R. The problem with R is that we don't know who R is. If I give you a number, you know it's real. But if I'm asking you what is a real number, can you tell me? In a constructive manner, like we say, what is Z? Well, Z is all the naturals and minus the naturals. What is Q? All the fractions from integer numbers. Well, what is R? What makes a valid quantity, and maybe there's some numbers that are not valid quantities. What is R?
Is it like a number that doesn't terminate?
Number that doesn't terminate? That's not very mathematical, right? I mean, he means to say it has many, many decimals, right? It's like, I think you mean 3.1257923, so on and so forth, and I can't write all the decimals. Is it true that all numbers that do not terminate are non-rationals? So if I have the number 1.99999999999, that never terminates. Is that a rational number? That is a rational number. That is 2. Do you guys do this in secondary school? 1.99999 is actually 2?
Yes.
If it doesn't terminate? Because the meaning of 9999, it's arbitrarily close to 2. It can't be any less than 2 because then it will terminate. So it doesn't terminate, that's 2. Is it true that all the numbers that do not terminate form the real numbers? Any real number can be written as a number that does not terminate?
I'm confused about how that doesn't fit into the table.
Who doesn't fit? We don't know what the real numbers are yet. All the numbers that do not terminate?
Yeah, because like eventually you'll get to that.
If it terminates, if the decimals are like 250 decimals and nothing after that, I'll get to the 250. But these numbers, like take pi, right? 3.1416, it never terminates. It doesn't have the last decimal. So no matter how far you go in the table, you're gonna never reach exactly that value because pi has infinite amount of decimal values. Yes?
I think a real number is a string of digits, x1, x2, and so on, from 0 to 9. And so if you like suppose that if there R is countable, then you have an infinite number of x1, x2, and so on, and you have so you make a table of that initially, and then you can show that it's not countable by choosing the first digit.
Correct.
Of that second digit.
Whatever mapping you built, there is a way to find a real number that's not in that mapping. Right. R is not countable. We still have the problem of what is R, and that's a problem for calculus, not for discrete math. R can be defined as the limits of all sequences of rational numbers. So if you pick sequence of rational number and you consider the limit of those sequences, those are the real numbers. Anyway, that was the last proof that he said. Build any mapping you want between n to q. He said, whatever mapping you want, 1-to-1 or not, I'm going to find a real number that's not the value of this mapping. That's the proof that he said. You build your mapping in any way you want. I have a way to get you a real number that is not mapped to anything. That means it's not countable. So that's something that you need to think about for a day or 2 or 3 and then maybe look it up online. It's a very fundamental result in mathematics because it shows that infinite sets are countable and not countable. Not all infinite sets are countable, which makes it in mathematics allow us to define different kinds of infinity. There is the countable infinity that corresponds to any set that's countable. And then there is some other infinities like R, the size of R, which is not the same as that infinity. There's a bigger infinity. All the countable sets have the same infinity size, the countable infinity. because they all map to one to each other. But these sets are not. Right. Yes?
Are there any infinities bigger than the not countable ones?
Correct. For any set you go, if this is a size, the size of this set is size of A, if you construct the power set, that's automatically a bigger size. So this power set, it's always bigger. Of course, it's bigger for finite sets, because if this has 3 elements, this has 8. If this is 5, this has 32. But even for infinite sets, if you start with a countable set and you build all subsets of it, that cannot be countable. And then R is a set, it has a certain infinite size. If I do the power set of R, I get a bigger infinite. In fact, R, the size of R is the same as 2 to the n. So if you build a power set for the natural numbers, that all the subsets, the set of all subsets of natural numbers, that has the same size as the set of real numbers. So that's something somebody smart can prove. Hey, the mapping 1 to 1 that I cannot build from R to n, I can build from R to the power set of n. And that's a bigger infinity than the countable one. And if I want an even bigger one, I do the power set of R and I get an even bigger infinity. Alrighty? Now we're ready to move on. Meaning moving back to the regular section. That's what we mean by moving on. So, how do we do induction? And how do we do sequences? Let's start with sequences. At first, it's of numbers. Here's A1. Let's say that's a 2. A2, that's a 4. A3, that's 6. A4, that is an 8. A5, that's a 10. Who is A6, do you think? That's the kind of question you might get. If I show you the first 5 elements in a sequence, what's the next one? Right? So that's a guess, right? I mean, it follows the intuition that you can tell what kind of sequence this is. And if you're to characterize in English this sequence, how would you say? What rule governs this sequence? Right, that's a general rule. I mean, really English. Like, I don't know what n and minus 1 is. How do I get from one element to the next? Add 2, right? This is the difference between any a n plus 1 minus a n is 2. That's a rule that governs this sequence. And because of this kind of rule, this is called an arithmetic progression. Or arithmetic sequence. And somebody said there is a general rule for it. I can give the general rule, who is an, as a function of n. What is the function that governs this? This is called the index. This is another index. So this is the index in the sequence, starting with 1. Sometimes you can start from 0 if you want, doesn't matter. So what's the rule that governs this sequence? You have a question? Or?
Oh, I was going to say what the rule was.
What? Tell me.
A sub 0 plus n times the difference.
How about 2n? Would that be easier? 2 times n is the value, right? Easy. I mean, his rule is more general, is correct. But I'm just saying, what you see is what you get. Isn't that 2n? All right. I will try a different one. I say 5, 8, 11, 14. What's the next one? What's the rule here? The difference, an plus 1 minus n, is 3, right? So the next one's gotta be 17, and the next one will be 20. And what is the rule in here? Who's AN? If I want to guess a general rule, what is it? 3n plus 2. So what's the general form of an arithmetic progression? It's some b term plus a times 1 is b plus 8 times 2, b plus 8 times 3. Generally speaking, is b plus 8 times the index, whatever the index is. So what is the difference? an plus 1 minus an will always be what? This a. Right? This is the arithmetic progression that jumps, is the jump between the values. And the general form would be b plus na. Those are, of course, very simple linear functions. And it's easy to see that a linear function corresponds to an arithmetic progression, and an arithmetic progression will always correspond to a linear function. So to find out the generative function, I need to find a and b. Any arithmetic progression depends somehow on a b, which is an offset. Everybody gets offsetted by b, b plus, b plus, b plus, and the a, which is the progression step. Okay, so that's a kind of sequence. Before I do induction, I wanna give you another one. See if you can. Another two actually. That's a general form here. Let's say, what if I have 1, 1 by 2, 1 by 4, 1 by 8, 1 by 16. What's the next one? 1 by 32. And what is the general, how do I write this progression step? What's the rule? It's not the difference anymore that does, it's a constant difference, like in here. In arithmetic sequences, the difference between elements is a constant. In here, what is a constant? What is a constant in this sequence? Obviously, the differences are not, right? What's the difference from here to here? From here to here? 1/8, 1/16. So the difference is not constant. But what is constant? The ratio. So the an plus 1 divided by an is always 1/2. So this is a geometric progression. And the rule for the geometric progression is an is what? In this case. Is it really 2 to the n? Every time you minus 1. You really have to check the index to be correct. You put n equal 1, because I start at 1, and say, okay, if n is equal 1, what do I need to put 0 to get a 1, not a 1? I don't want to start with the wrong value. Right? How about if I have 1, 3 squared, that's 9, right? 27, 81, what's the next one?
343.
343.
243.
What's the rule here? An plus 1 by an is always 3. And the rule is an is 3 to the n minus 1. Let's do another one. Suppose I start with 7, and this one is 28, and this one is I don't know, 10. How much do I need? 12. What's the next one? 1, what's going on here? What am I doing? I started with something which is not 1, and I multiply by 4 all the time. So how much will this be?
1792.
How much?
1792.
Like that? I don't know, is that correct? Maybe. So what's the rule here? But this is not 4 to the n minus 1, right? Because it doesn't start with 1.
It's 7.
It's something else. It's what is it?
It's 7 times 4 to the n minus 1.
Right? That's what it is. It's 7 times 4 to the n minus 1. All these are geometric progressions. Let me show you one more. That's actually more related to this one here than to the one here. How about this? 1, 3, 6, 10, 15. Guess what the next number is?
21.
Why? 21, why? What's the rule? Okay, I can agree with 21 if somebody explains me what's the rule. Is the difference constant? No. Is the ratio constant? So it's not one of those. It's a different kind.
It's an plus 1 minus an equals n. That's like the arithmetic progression.
What? Say again? An plus 1 minus an equal with what?
Like it'd be a plus n every time. You'd add n to the previous number.
I think you mean to say it's one of these.
Yeah.
It's an arithmetic progression.
Yeah.
Is that the rule you guys applied when you say 21? How somebody got 21? How did you get 21? Huh? Add 6, but why 6 and not 20?
It's the 6th.
Because it's the 6th element? No, that's not the reason for the 6. It's a coincidence. The reason to add 6 is that before 6 I added, and before 5 I added, and before 4 I added. So if I do the delta here, an plus 1 minus an, this is nothing because it's the first one. How much I added here? 2. How much I added here? How much I added here?
4.
5, 6. Is this an arithmetic progression now? So the arithmetic progression is in the difference between them. It's not between the numbers themselves do not form an arithmetic progression, but their difference forms an arithmetic progression. So what is the general rule for this thing? Who is this? If the numbers form an arithmetic progression, we know they look like this. Some constant times n plus an offset. Because those are the arithmetic progressions. But now, the numbers look in such a way that their differences form an arithmetic progression. So they're definitely not like this. How can I make some numbers in such a way that their difference forms an arithmetic progression? What would be the general rule? Or you can guess the general rule just by looking at the numbers if you want. Yes?
I mean, this is just the sequence of, I think this is called triangular numbers, right?
What? I can't hear.
Isn't this the sequence of like triangular numbers or whatever, so it's just,
Triangular numbers?
I don't know if that's what it's called, but.
I don't have anything in my notes with triangular. It may be.
But anyways, n times n plus 1 over 2.
Okay, so he has a formula, n times n plus 1 over 2. We can check that formula. Is that true? So n in here is 6. 6 times 7 over 2. Is that, maybe it's 1. It's shifted by 1, right? It's n times n minus 1 over 2. So would that work? Or maybe I missed a number? 1. This is the third one, fourth one, fifth one. That's right. So it's n times n plus 1 over 2. Okay. This is a quadratic sequence. And the general form, which is correct in this case, it's something like an squared plus bn plus c. So instead of being a first degree equation, like 3n plus 2, is a second degree equation. So if I know it's n squared plus n divided by 2, can you tell me which ones are a, b, and c to get this exact form? A will have to be 1/2, n coefficient will have to be 1/2, and the c coefficient is 0. So every time we get a quadratic sequence, it's the one that if I take the differences, I get an arithmetic sequence or progression. And there is a very good reasoning for why this property, that if I take the differences, I get arithmetic, results immediately in a quadratic thing. That comes from calculus. Those two things are the same thing said with 2 different words. One thing is to say, if I take the differences, I get an arithmetic progression. And the other thing is, this is quadratic, which is in a certain relation with the arithmetic sequence, which is linear. What is the calculus property that I need here to show off this thing? Yeah. Which one is it? The derivative from calculus, the differential, applied to discrete becomes what?
For a rate of change.
If I apply to continuous,
Comes the delta.
I get what?
The delta.
The difference. If I differentiate this, I can't really differentiate it because it's not a function, it's a discrete sequence. But if I apply the mechanism of differentiation to it in a discrete sense, I get the deltas, right? That's how differentials work. It's a limit of f of x minus f of x plus a constant there. So what happens when I differentiate a quadratic equation? I get a linear equation back, right? That's why quadratic sequences, when I take the difference, I get exactly the ones that correspond to taking the differential of this, I would get this. In fact, I can find out a, b, and c that way. Here's how. I take the deltas, and now I figure out what is the form that I need here. What linear form corresponds to this? So if this is a n plus b, who's a and who's b? Right, so this is n. A equal 1 and b equals 0 will give me the form required to this. Now, I'm looking for a quadratic equation that differentiates to this thing. What coefficients I need to differentiate? So what a n squared plus b n plus c differential will correspond to 1n plus 0. Why don't you try this exercise? The coefficients that I need in this polynomial, so that when I differentiate, I get this arithmetic sequence, are going to be exactly the coefficients that my quadratic sequence has. We'll have to get to it a little bit next time. It's not essential to know this, but it's much faster way to solve problems during the quiz. If I give you a sequence and I'm asking you, what are the coefficients? That may be a hard way to get them, but if you transform it into an arithmetic sequence, get those coefficients and integrate back, it's a faster process. So now, let's see if we can sum up some of these sequences. So sums. Sums of sequences, that is. How can I do if a n equal n, that would be the sequence 1, 2, 3, up to say n, a k equal k. How do I do this sum? Sum of first n elements in sequence. I can write this as sum from k equal 1 to n of ak, or I can write it as enumeration 1 plus 2 plus 3 plus n. How can I sum this up? I have three ways of doing this. Figure out the sum. First of all, how many people know the answer to this question? Okay, this is a very simple answer that you can probably figure out without a lecture. If I tell you sum of these numbers, you probably can figure out what it is. So here's the first option to solve this problem. I do my sum here is 1 plus 2 plus 3 plus n minus 2 plus n minus 1 plus n. I write the same sum in reverse. N plus n minus 1 plus n minus 2 plus 3 plus 2 plus 1. I now sum it up part by part. So 2 oranges here, right? Because each one of them is an orange. How much is n plus 1? That's n plus 1. How much is 2 plus n minus 1? That's another n plus 1. How much is 3 plus n minus 2? Everybody can see this, that 3 plus n minus 2 is an n plus 1. Plus. In here, what do I get? N minus 2 plus 3, how much is this? N plus 1 plus n plus 1 plus the last one is n plus 1. So now I look at my summation and I say, how many n plus 1s do I have here? N of them, right? So that's got to be n times n plus 1. But this is 2 oranges. So how much is an orange? Divide by 2. This is a neat trick. Some people call the Gauss trick, but it's not really a good way systematic way to approach the sums. To try to figure out this trick for a random sum is quite hard. But this is kind of a direct proof that's, say, easy to do without induction. Here's another way to do the same thing. Another way is to figure out, so this is a summation proof 2. Didn't we just figure out who AK is? AK is K, which is 1 times K plus 0. That is in arithmetic form. This is not really a proof for this exercise, but will serve as a proof for any arithmetic sequence. What this does is says, let's assume we know this formula. The reason it's not a proof here is that this formula is exactly what I'm trying to prove. But it will work for any arithmetic sequence from now on. The trick is to say, I want the sum of AK from k equal 1 to n. I'm going to break it into sum of 1k plus 0 from k equal 1 to n, which is 1 times sum of the k from k equal 1 to n plus 0. So this is n times. The right way to show you how this works is to do a different arithmetic progression and to show it to you there. So suppose I take this one here. So I have AK is the sequence from k equal 1 further, 5, 8, 11, 14, 17, 20. Somebody asked me to do the sum from k equal 1 to n of AK. If I apply this trick, I have to get first the formula for the arithmetic progression. I'm going to say this is a sum from k equal 1 to n of 8k is that formula over there, 3k plus 2. Is that correct? Every 8k is actually 3k plus 2. So this is 3 times the sum from k equal 1 to n of k plus 2. Now if I know the formula for the basic arithmetic progression, which is here, that's going to be 3 times n plus 1 by 2 plus 2. Because this sum is the first sum we already computed. It's right here. So the most useful ways, the fastest way, and the most systematic way to approach all this sum and product and properties proving with all these sequences is to replace the sequence with this general form, if you know it. That's what I would do without blinking at any question that asks me about the sequence. Here's a sequence, you want to prove something about it, you want to sum it up, you want to differentiate it, you want to find whatever. The first thing I would do, I replace the sequence with a generic form, if I know the generic form. Because see, when the sequence is given to me, I don't necessarily know immediately the generic form. But as soon as I know it's 3k plus 2, I replace the 8k's with 3k plus 2 everywhere, and then I do my calculations in that form. That is the most systematic way to solve any problem quite fast. Okay? So the third way is to introduce induction. The third way is to notice that our first induction problem is to notice that these sums are very related to each other. In other words, if I call this Sn 1 plus 2 plus all the way to n, and Sn plus 1 is 1 plus 2 plus all the way to n plus n plus 1, right? The terms that I'm summing, a lot of them are in common, right? So I can say Sn plus 1, the sum for the next n, the next value, is really the previous sum plus one more term. Right? If you want to sum up to 101, that's effectively summing up to 100 and then adding 101 to it. So what we want to use here is, wait a minute, we already know Sn. I mean, presumably we computed it before. If I know Sn, can I compute Sn plus 1 by saying, replace Sn with what I have, n times n plus 1 by 2, and then add n plus 1 to it. In other words, this is my Sn. I want to get everybody to focus on what's going on here. I have a new way to compute in this sum. But this is kind of a recursive way. It's saying you want the sum all the way to n plus 1. What you have to do is to get the one up to n, compute that one, and then just add n plus 1 to it. We've seen this in the factorials, right? N plus 1 factorial was nothing else than n factorial times n plus 1. That's the same thing happening here. But in here I'm going to say I already know who Sn is. Is n times n plus 1 by 2, because I already done it here. So if I want n plus 1 to that, I'm going to get something like n plus 1 times n plus 2 by 2. So this is the core phenomena in induction, which we need to formalize. How do we say you can obtain Sn plus 1 from Sn and an additional step? That's what's going on in here. So how are we going to say that? This is not a formal induction. This is just like scrap paper induction. So here's what we're going to do. We're going to say proof by induction. We want to first have a statement. In induction, statements are indexed. When I make a statement, it's a statement for a particular n value. And this is the induction index. Induction index. So I'm going to make a statement for n, which is to say Sn, which is, my Sn here was 1 plus 2 plus 3 plus n. This is n times n plus 1 by 2. Now this is not something I already know. This is something I want to prove, right? So this is 1. Now, this statement, logically speaking, it's a true or false thing, right? This is either true or false, and there is theoretically the possibility that it might be true for some n's and not true for other n's. So what we actually want is statement of 1 and statement of 2 and all of them. We want to prove that all these statements are true because this has to be for any n, right? Bigger than 1, I guess. So what we want to do here is another, effectively what we want to produce statement of 100 and so on and so forth. We want to show that all these statements are true. Each statement is indexed. It corresponds to a particular property. So how would the statement for 75 look like? That property for n equals 75. It's what? 1 plus 2 plus 3 plus 2. 75 must be equal with? So every one of these statements is a logical property. It's either true or false, right? And the statement is general, is statement of n, and every time you plug in an n, you get a different statement. Now, of course, all of them are true. We know that from the other proof, because this doesn't matter what n is, you're always going to get these values. So here's how the induction proof goes. Let's say idea is first proof the statement of 1. We call this base case. And then prove that statement of 1 implies statement of 2, implies statement of 3, implies all the way to the end. That's how induction goes. It says you want all of them to be true? Prove the first one manually. So by the way, what is statement of 1? What is this saying? If I'm to translate it, plug n equal 1, I get what is the actual statement? 1 equal to 1 times 2 divided by 2. Right? Can everybody see that if I write this statement as n for n equal 1, I get 1 equal 1 times 2 divided by 2. Hands up, who's with me? Good. So this I can prove manually, right? I don't need anything to prove this. But then induction says you got to prove this one for sure to be true first. And then from here, prove the next one. And from here, prove the next one. And from here, prove the next one and the next one. And everybody implies the next one. Now, how many proofs are here? A lot of proofs, right? We don't want to do these proofs separately. I mean, you could. You say, if this is true, then this is true. And if it's true for 2, what's the statement for 2? 1 plus 2 equal with 2 times 3 Divide by 2, right? What's the statement for 3? 1 plus 2 plus 3 equal with?
3 times 4.
Right? So we could prove little by little from here to here. And now, since this is true, this gotta be true. Remember, implication, if I start from true, this one has to be true. And then from here, I prove from here to here. If this is true, then that is true. And if this is true, then that is true. Eventually, I prove all of them. But instead of proving them separately, I can prove them all together generically. Like instead of proving statement of 1 implies statement of 2, and separately from 2 I get to 3, how about I write a general implication? I say statement of any k implies the statement for k plus 1. For any case. If I do this for any k, isn't it the case that I proved all of them together? Because for various k's, I get various implications. If k is 2, I get this implication here, from 2 to 3. If k is 1, I get this implication here. If k is 75, I get what? From 75 to 76. If k is 100, I get from 100 to 101. So my idea here for induction is to say, instead of proving them one by one, I'm going to prove all those steps at once for a general k. And my claim, this is called an induction step. And you have to write it down explicit. Any induction proof has to explicitly state which one is the induction index. When you say induction, that's incorrect. You're going to lose points immediately. You have to say induction by n, induction by k, induction by who is the induction variable. And then when you write the induction step, before you prove it, you have to state what does that mean. What does it mean? It means that if sk is k times k plus 1 by 2, implies the next sum is going to be who? What is this for k plus 1? This value here.
K plus 1 into k plus 2.
So before you prove it, you have to state what the induction step is. The induction step for my case is that if the sum for k numbers, the first k number is this, then the sum for k plus 1 numbers is that. That's not a proof. It's just I'm stating what is my induction step. It's not enough to say induction step is statement of k implies statement k plus 1. That is true in all induction proofs. You have to state for this problem what is the induction step, from where to where. Okay, so how do we prove this? Now, as a direct, once you get to here, you can forget about induction. You just prove that. So how do we, if the sum of the first k numbers is really k times k plus 1 by 2, how do we get the sum of the k plus 1 numbers? Yes?
Would you substitute k plus 1 into k?
Right, so I can just say, how do I prove this? I say, who's sk plus 1? Sk plus 1 is just sk plus k plus 1, right? We already made this proof right here. That was the induction step. Now, I know who sk is. Logically speaking, why do I know who sk is in this whole induction step? What allows me to say I know sk? Not the base case. The induction premise, right? In this implication here, like in every implication, we have a premise and a conclusion. I know sk because it's part of the premise. It's given to me in the induction step. Right? So I can substitute that with k times k plus 1 by 2 plus k plus 1. And you can do the calculations here. It's very easy to show. This is k plus 1 times k plus 2 by 2. which proves my induction step. It says, if you knew this is sk, then sk plus 1 is this value. So that proves all these implications. Instead of doing them one by one, it does all of them at once for a generic k. If I want one of them, I just substitute k with 3, and I get from 3 to 4. How many people with me? It's pretty easy when somebody else is saying it. Yeah. So how about that geometric series? How does one sums geometric series? So in here we sum up the basic arithmetic series, and we say that any other arithmetic series, if I know its generic form 3n plus 2, I can just call 3n plus 2, use the sum, right? The geometric series, the general form is AK is, I think, B times R to the K, or K minus 1. So if you remember, the ones that we have before all have this property. They start at the B and they multiply with the R. So if B is 2 and R is 1 over 3, what do I get? What's the sequence AK? K equal 1, K equal 2, so on and so forth. The first one is 2, right? The next one is 2 by 3. The next one is 2 by 9, 2 by 27, up to 2 to the 3 to the K minus 1, that's AK, and then so on and so forth. So how do I sum up? The question is the sum of first n elements in a geometric series. So that would be 2 plus 2 to the 3 divided by 3, 2 divided by 9 plus 2 divided to 3 to the n minus 1. Right? So you can think of this as 2 divided of 3 to the 0. How do I do this? Like in the arithmetic sum, we have this trick, 1 plus 2 plus n is n times n plus 1 by 2, that we can use to solve any arithmetic progression. In here we have a trick too. The trick in here is r, 1 plus r squared plus r cubed plus r at n minus 1. Anybody knows the formula for this? It's r at n minus 1 divided by r minus 1. How many people knew this formula before today? One. Quite a few. Okay. That is if r is not 1, because if r is 1, I can divide with 0 here. So it's true for all the numbers except r equal 1. If we knew that, this is very easy, because we call it sum from k equal 1 to n of ak. That's the sum of the first n elements. We know the generic form. It's sum from k equal 1 to n of ak is b times r at k minus 1. The generative form of it. Now b goes in front of the parenthesis here. K equal 1 to n of r to the k minus 1. That's exactly this sum here. Okay. This is b times 1 plus r squared plus r to the n minus 1. It's exactly that sum. So I can replace with that formula and I get b r minus 1, r at n minus 1, r minus 1. That's again if r is not 1. If r is 1, do I need a formula for this? What is it? How much is this whole thing if r equal 1? N, right? So if r equal 1, I can do it manually. If r is not 1, I apply the formula. And I've got any geometric series, the answer to it. But why is this true? Let's prove these things. Let's call this whole thing M. Right? Anybody knows the proof of this?
The inductive one or the other one?
The other one.
Yeah, so if you divide m by r.
I like to multiply.
Sure.
I do r times m. What do I get? I'm going to align it. 1 becomes r, right? When I multiply by r. But I'm going to align it a little bit in here. R plus r squared. So this 1 becomes r becomes r squared, r cubed. And the last one, r and then minus 1, when I multiply by r becomes
Rm.
r to the n. Everybody can see this, that if I multiply this whole sum with r, I get r squared, r cubed, r fourth, rn minus 1, and the next one, rn. So now what do I have to do to get something interesting? Between those two, to get something interesting, I do what? That's the kind of step that you need to push through in a proof. I've got this r times m, and I got m, and they have a lot of common terms, right? What operation will allow me to get rid of all of them? Almost all of them. A subtraction, right? So if I do rm minus m, this is the first one, I subtract this one from it. Who goes away with who? Everybody goes away, except from the rm, I'm left with r to the n. And the other guy that is subtracted from is left with what? The 1, right? So now who is rm minus m? Is m times r minus 1, right? So now if r is not 1, if r is 1, I can't do anything about this. I'm done. But if r is not 1, I can obtain m as r to the n minus 1 divided by r minus 1. How many people follow me here? Okay? This is the same idea that we did for the arithmetic basic progression. It's not here anymore. The one that was 1 plus 2 plus n, and then we wrote it backwards, n plus n minus 1 plus 1, allows us to do an operation to get the same term. The operation there was addition. Now, again, we manipulate it and do a subtraction, and I've got my formula. How would the proof by induction look like? The same property. So I'm going to use this stuff in here, and I'm going to say my statement is not that anymore. My statement is here is what? Is this mn 1 plus r squared plus r to the n minus 1 is r minus 1, r at n minus 1 divided by r minus 1 if r is not 1. So r is a constant, is the geometric step. So it could be 2 or 1 over 2 or 3 or 1 over 3 or 25 or 1 over 25, but it's a constant. What is my induction step? It's that if mn is r to the n minus 1 by r minus 1, then what?
Mn plus 1.
M, the next statement, mn plus 1, is r to the n plus 1 minus 1 divided by r minus 1. In other words, it says, if this formula works for 25, it's also going to work for 26. If it works for 35, it's going to work for 36. It's the same implication, all those statements, one after the other. And I need a base case. I don't want to talk about base cases today, so I'm going to save that for Tuesday, base cases. But we always need to prove the first statement. So how do we do this proof? Again, in those proofs, this is my premise. And this is my conclusion. So I can use this fact in an induction step. I'm assuming I already know it works for n. I'm proving it for n plus 1. Who is n plus 1? Is 1 r squared. Same idea, r to n minus 1 plus r to the n. Right? It has one more term than before. Now this part in here, it's exactly mn, right? The first n of them. That was the previous one. Plus the last term. So now I'm using the premise to say I know who this mn is. This is r to the n minus 1 divided by r minus 1. Right? Right here. I'm adding to it r to the n, so what do I get? How do I manipulate fractions here? This is r to the n minus 1 plus r minus 1 times rn divided by r minus 1. So what's that, that numerator there? R to the n minus 1 plus r to the n plus 1, I think. R times r to the n. Minus, how much is this minus 1 times rn? Rn divided by r minus 1. Now r to the n goes away with r to the n. So I'm left with r to the n plus 1 minus 1 divided by r minus 1. That's what I wanted to do. Not all induction proofs go the same way, but all induction proofs have an induction step implication. From the previous, go to the next. And the previous is what we already know, so we can use it. One more thing, what would be the base case in here? Again, I don't want to talk about base cases today, that's what we're going to do next week. But what would be the base case today? Who is M1? What is the statement? Statement of 1. Statement of 1. Is M1, which is just 1, has to be equal to who? R minus 1 divided by? Is that correct? So the base cases, the reason we're going to leave it for the end is that they're a little bit complicated sometimes, but we always need them.
I need to shower. Like I came right from the gym and then I was like, and then you shoot in here.
See, basically all I did was yesterday because I managed to fire myself in
I'm really tired when I sleep. I was better like
I think it works what you have to say. I think we follow your argument. But
lecture because I don't
if I say now I think your argument is at the same time, they have to have the same argument. So whatever the factorization is, some power, whatever, this, whatever the factorization is, they have to be. Right? And we have to get it back here because now, since A doesn't have anything common with B, all the factors in A must appear where? Right? All the factors in A. Since there's nothing common with B, all the factors in B. Then the factors in C, since there's nothing common with D, must appear where? So then C must appear. I think that's a more formal way to say it. I think you're right, yes. Bring it to the rest.
I don't want to walk in the
That's fine. That's fine. Don't worry about it. Bring it there. I'm sure you're going to get all the attendance. Because if I get it taken now, I'm going to lose it before. But you can tell the TA you're not late or anything. You just forgot to submit it. Is that okay? You're coming next week, right? At the station?
I'll be here.
Yeah. Why? No, you're not going to lose any points for that. You guys have any questions?
Thank you.
Did you prove, anybody else prove the coprime stuff? If A by B is equal C by D, and they coprime, they have to. Is it hard?
So if you
Say it to me.
if A over B equals 0